Welcome to Professor Mad. If you're struggling with Thevenin's theorem, you must watch this video. We cover all the basics, starting with what Thevenin's theorem is and why it's so important. We'll walk through all three types of Thevenin problems step by step. By watching until the end, you'll gain the skills and confidence to solve any problem involving Thevenin's theorem. What is Thevenin's theorem? Here's the idea. No matter how messy a circuit looks with multiple resistors, voltages, and connections, we can simplify it to just two things: a voltage source and a resistor. The voltage of this source is called the Thevenin voltage. This is the voltage we measure across the load terminals when there's no load connected, like an open circuit. Resistance of the resistor is called the Thevenin resistance. This is the resistance seen by the load when all voltage sources in the original circuit are turned off or set to zero. By calculating these two things, Thevenin voltage and Thevenin resistance, we can turn a complex, messy circuit into a simple, two-part circuit that's much easier to analyze and work with. Let me explain why Thevenin's theorem is so important with a simple example. Imagine you have a circuit that powers a light bulb. Now, what if you have several light bulbs, each with a different resistance? You want to figure out how much current will flow through each one, because the brightness of the bulb depends on how much power it consumes, and power depends on both the current and the voltage. Sure, you could use Ohm's law and Kirchhoff's laws to solve the circuit for each bulb individually, like this. But that's time-consuming and involves a lot of repetitive work. Now imagine you had 100 different bulbs to test. Doing that manually for each one would be a total nightmare, right? This is where Thevenin's theorem comes to the rescue. Thevenin showed us a shortcut. Instead of recalculating the entire circuit every time you change the bulb, you can simplify the whole circuit into just one voltage source and one resistor. This new simplified circuit makes it super easy to figure out the current and voltage for any bulb you plug in. This was a huge breakthrough because it saved tons of time and effort, making circuit analysis way more efficient. Thevenin's theorem shines in scenarios where you want to see how the circuit behaves when one component changes. It dramatically reduces the number of steps, saving you a lot of time and effort, especially when dealing with complex circuits or multiple changes. The whole point of learning Thevenin's theorem is to master how to simplify circuits by calculating the Thevenin voltage and Thevenin resistance. Once you've got those, analyzing the circuit is a breeze. Before diving into Thevenin's theorem, it's important to be comfortable with some basics, especially Ohm's law and Kirchhoff's laws. These are the foundational tools you'll need to understand how currents and voltages behave in circuits. If you're not familiar with them, make sure to check out our previous videos. I'll include the links in the description. Before you can apply Thevenin's theorem, you need to figure out what kind of power sources your circuit contains. Power sources can be categorized into two types. Voltage sources create a potential difference in the circuit, driving current through the components. Current sources establish a fixed current that flows through the circuit, regardless of the voltage across them. Both voltage and current sources can be divided into two categories: independent sources, which provide a fixed voltage or current, unaffected by anything else happening in the circuit; dependent sources, which the output depends on other elements in the circuit. Before you can apply Thevenin's theorem, you need to figure out what kind of power sources your circuit contains. This helps you choose the correct approach for simplifying the circuit and solving it efficiently. We can categorize circuits into three types based on the type of power sources they contain: circuits with only independent sources, circuits with both independent and dependent sources, and circuits with only dependent sources. Let's discuss one by one. To solve circuits with only independent sources using Thevenin's theorem, follow these steps. First, disconnect the load. Remove the load resistor. This isolates the portion of the circuit you're simplifying. Secondly, we can calculate Thevenin voltage. Use Ohm's law and Kirchhoff's laws to find the open circuit voltage across the terminals where the load was connected. This voltage is called the Thevenin voltage. Next, deactivate the sources. Short-circuit any voltage sources. Replace them with a wire. Open circuit any current sources. Remove them, leaving a break in the circuit. After deactivating the sources, we can calculate the Thevenin resistance, calculate the total equivalent resistance across the open load terminals. Combine resistors in series or parallel as needed to get the total resistance. Since now we have both Thevenin's resistor and voltage, we can draw the Thevenin equivalent circuit. Finally, we have a simple circuit. We can easily calculate the voltage and current for any load resistance using Ohm's law. This is our first example. Find the Thevenin equivalent circuit for the load in the given circuit. Calculate the load current and power for the following loads. The goal of problem is to find the power consumption of each light bulb when connected to the circuit. This circuit only contains independent sources, a single voltage source. Let's follow the mentioned steps. First step is disconnecting the load. Remove load resistance and keep the nodes A and B disconnected. Now we can analyze the circuit without the influence of the load. Now we can calculate the voltage across the nodes A and B. This is the Thevenin's voltage. Current will not flow in the 8 ohms resistor as it is open. So the voltage across the nodes A and B is equal to the voltage across the 4 ohms resistor. Now the circuit just contains one loop. We can solve this just using Ohm's law. If we have more than one loop, you may have to use Kirchhoff's laws as well. Current flowing through the loop is equal to the voltage divided by resistance. We get the current as 3 amperes. Now we can again use Ohm's law to calculate the voltage across the 4 ohms resistor, which is 12 volts. Therefore, 12 volts will appear across the AB terminals. This is the Thevenin voltage. Our next goal is to calculate the Thevenin's resistance. For that, we have to deactivate all sources. That means deactivate all independent voltage sources by shorting them. Deactivate all independent current sources by opening them. Here we only have a voltage source, so let's short it like this. After deactivating the sources, we can calculate the total equivalent resistance across the open load terminals. This is our Thevenin resistance. To calculate the resistance, we combine the resistors in series or parallel as needed to find the total resistance. In this case, the 4 ohm and 12 ohm resistors are connected in parallel. By solving for their equivalent resistance, we simplify the circuit. First, we calculate the total resistance of the parallel connected resistors. R1 is equal to 3 ohms. Next, R1 is in series with the 8 ohm resistor. Adding them gives us a total resistance of 11 ohms. This is the Thevenin resistance of our circuit. Now that we've found the Thevenin voltage and Thevenin resistance, we can move on to the next step. Let's draw the Thevenin equivalent circuit. To finalize the Thevenin's theorem process, let's calculate the current for a load with resistance R. Using the simplified Thevenin equivalent circuit, we can easily calculate the current through the load using Ohm's law. We have found the Thevenin equal circuit. It may seem like a lot of work initially, but once you're familiar with the process, you'll be able to reduce the number of steps and solve circuits quickly and efficiently. We've simplified the original circuit into a much simpler one, consisting of just a power source, a resistor, and the load. This Thevenin equivalent circuit can now be used for further analysis, eliminating the need to work with the original complex circuit. Let's calculate the power for each load. For 5 ohm load, the load current is 0.75 amperes. The load power is 2.81 watts. For 7 ohm load, the load current is 0.67 amperes. The load power is 3.14 watts. For 9 ohm load, the load current is 0.6 amperes. The load power is 3.24 watts. After developing the Thevenin equivalent circuit, we can easily observe how the load current, voltage, and power change for any number of load resistors. Instead of recalculating the entire circuit each time, we only need to adjust the load resistor in the simplified circuit. Let's try another example. Find the Thevenin equivalent circuit for the load in the given circuit. Calculate the load current and power for the following loads. This circuit only contains the independent sources, 2 voltage sources, so this should be solved under the case 1. First step is disconnecting the load. remove load resistance, and keep the nodes A and B disconnect. Now we can analyze the circuit without the influence of the load. Now we can calculate the voltage across the nodes A and B. This is the Thevenin's voltage. This circuit contains only one loop, so you could use Ohm's law directly to find the current. However, for demonstration purposes, I'll use Kirchhoff's voltage law. Start by summing the voltages of the sources and the drops across the resistors. The current flowing through the loop is calculated as 0.33 amps. Then the voltage across the points A and B is equal to the voltage of the power source minus the voltage across the resistor. You can calculate from either side. I'll go from the 10-volt source side. We get the voltage as 13.33 volts. This is the Thevenin voltage. Our next goal is to calculate the Thevenin's resistance. For that, we have to deactivate all sources. That means open current sources and short voltage sources. Since we only have voltage sources, let's short-circuit those. After deactivating the sources, we can calculate the total equivalent resistance across the open load terminals. This is our Thevenin resistance. Now we have to calculate the resistance across the points A and B. If you look carefully, you will see that both resistors are connected parallelly across the point A and B. So we can calculate the total resistance, which is 6.67 ohms. This is our Thevenin resistance. Now that we've found the Thevenin voltage and Thevenin resistance, we can move on to the next step. Let's draw the Thevenin equivalent circuit. To finalize the Thevenin's theorem process, let's calculate the current for a load with resistance R. Using the simplified Thevenin equivalent circuit, we can easily calculate the current through the load using Ohm's law, eliminating the need to work with the original complex circuit. Let's calculate the power for each load. For 30-ohm load, the load current is 0.36 amps. The load power is 3.88 watt. For 40-ohm load, the load current is 0.29 amps. The load power is 3.36 watt. For 20-ohm load, the load current is 0.5 amps. The load power is 5 watts. Let's try another example. Find the Thevenin equivalent circuit for the load in the given circuit. Calculate the load current and power for the following loads. This circuit only contains the independent sources, a voltage source and a current source. So this should be solved under the case 1. First step is disconnecting the load. Remove load resistance and keep the nodes A and B disconnect. Now we can analyze the circuit without the influence of the load. The second step is calculating the voltage across the nodes A and B, which is the Thevenin's voltage. Here, no current flows through the 1 ohm resistor, so the voltage across A and B is equal to the voltage across the current source and 12 ohm resistor. Now mark the currents in each branch. Since the current source supplied 2 amps, the I2 is equal to 2 amps. Let's apply Kirchhoff's laws to the circuit. First apply the KCL to node X, then we can apply the KVL to loop 1. If you are not good at Kirchhoff's law, please watch our Kirchhoff's law video. The I3 is equals to 2.5 amps. Using I3, we can calculate the voltage across the 12 ohms resistor, which is 30 volts. This is the Thevenin voltage. Third step is disconnecting the sources. Here we have to short-circuit the voltage source and open the current source like this. Now we can calculate the Thevenin's resistance. Let's calculate the resistance between A and B. We can see the 4 ohm and 12 ohms resistor are connected in parallel. So let's solve it first. Finally, we can solve the series connected resistor. The total resistance is 4 ohms. This is our Thevenin resistance. Now that we've found the Thevenin voltage and Thevenin resistance, we can move on to the next step. Let's draw the Thevenin equivalent circuit. To finalize the Thevenin's theorem process, let's calculate the current for a load with resistance R. Using the simplified Thevenin equivalent circuit, we can easily calculate the current through the load using Ohm's law, eliminating the need to work with the original complex circuit. Let's calculate the power for each load. For 6 ohms, the load current is 3 amps. The load power is 54 watts. For 16 ohms, the load current is 1.5 amps. The load power is 36 watts. For 36 ohms, the load current is 0.75 amps. The load power is 0.9 watt. Now let's talk about the second case. To solve circuits with both independent and dependent sources using Thevenin's theorem, follow these structured steps. First, remove the load resistor to isolate the circuit and focus on finding the Thevenin equivalent across the load terminals. Next, use Ohm's law and Kirchhoff's laws to calculate the variable controlling the dependent sources. This is important because dependent sources rely on other circuit parameters. Now we can calculate Thevenin voltage same as earlier. This is the open circuit voltage across the load terminals A and B after the load is removed. Next, short circuit terminals A and B by connecting them with a wire. Recalculate the variable term for any dependent sources to account for this new condition. After that, calculate the short circuit current flowing from A to B. Now use the short circuit current and the Thevenin voltage to calculate the Thevenin resistance. With Thevenin voltage and Thevenin resistance calculated, you can now draw the Thevenin equivalent circuit. It consists of a single voltage source in series with a resistor. Now that the circuit has been simplified to a Thevenin equivalent, you can connect any load resistor to this circuit and easily calculate the voltage across and current through the load using Ohm's law. This process efficiently handles circuits with both independent and dependent sources, allowing for easy analysis of the load's behavior. Let's discuss an example. Find the Thevenin equivalent circuit for the load in the given circuit. Calculate the load current and power for the following loads. Here, the circuit contains one independent voltage source and one dependent voltage source, so this shall be solved under the case 2. Remove load resistance and keep the nodes A and B disconnected. Now we can analyze the circuit without the influence of the load. The next step is to calculate the variable term Vx, which controls the dependent sources in the circuit. In this example, the voltage of the variable source is depend on the voltage across the resistor R1. Since the circuit contains only one loop, the current flowing through the circuit is the same for each component in the loop. The total current flowing through the circuit is equal to the current flowing through the resistor R1 and any other resistors in the loop. Using this relationship, we can calculate the value of the variable. Vx is equal to 3 volts, so the voltage supplied by the variable source is 6 volts. Now we can find the Thevenin voltage by the usual circuit analysis methods. I'll apply the KVL around the loop. We get the current through the loop as 3 milliamps. Now using this current, we can calculate the voltage across the node A and B, which is 9 volts. This is our Thevenin voltage. Now we short circuit terminals A and B and calculate the current flowing through the short circuit. Remember, since we've changed the circuit by adding a short circuit, the variable term Vx we calculated earlier is no longer valid. We need to recalculate it. We can apply KVL to loop 1. This loop contains the resistors and the independent source. We get the current through the 1 kiloohm resistor to be 12 milliamps. Using Ohm's law, we get the voltage across this resistor is 12 volts. If you are skilled in circuit analysis, you may quickly observe the circuit and determine that Vx without going through detailed calculations. Next, apply KVL to loop 2. By solving KVL for this loop, we find the current I2 flowing through this loop to be 24 milliamps. Now apply KCL at node X, where the currents from different components meet. We find that the current I3 is 36 milliamps. This is the short circuit current flowing between terminals A and B. These recalculated values allow us to now compute the Thevenin resistance in the next step. In circuits with both independent and dependent sources, the Thevenin resistance is calculated by dividing the Thevenin voltage by the short circuit current, so the Thevenin resistance is 250 ohms. Now that we have both the Thevenin voltage and Thevenin resistance, we can construct the Thevenin equivalent circuit and analyze it for any load. Finally, let's calculate the load current for load with R resistance. When dealing with circuits that contain both independent and dependent sources, the process for finding the Thevenin equivalent involves two main steps. First, calculate the variable term controlling the dependent sources with terminals A and B open to determine the Thevenin voltage. Second, to find the Thevenin resistance, short-circuit terminals A and B, calculate the short-circuit current, and then divide the Thevenin voltage by this short-circuit current. This method allows you to simplify complex circuits for easier analysis. Since now we have the Thevenin's equal circuit, we can test the circuit for any load. Let's calculate the load current and power for given loads. For 300 ohms, the load current is 16 milliamps. The load power is 77 milliwatts. For 200 ohms, the load current is 20 milliamps. The load power is 80 milliwatts. For 100 ohms, the load current is 26 milliamps. The load power is 68 milliwatts. Our third and final case involves circuits that only contain dependent sources. To solve these problems using Thevenin's theorem, follow these steps. Disconnect the load at terminals A and B. Connect a test source across terminals A and B, either a 1-volt voltage source or a 1-amp current source. If a 1-volt voltage source is connected, calculate the current supplied by the source, then find the Thevenin resistance by using the test current. If a 1-amp current source is connected, calculate the voltage developed across the source, and then determine the Thevenin resistance from the test voltage. Since there are no independent sources in the circuit, the Thevenin voltage is always 0 volts. The final Thevenin equivalent circuit will contain only the Thevenin resistance. Solving circuits with only dependent sources is relatively straightforward. With no independent sources present, Thevenin voltage is always 0 volts, and the task is simply to use a test source to calculate the Thevenin resistance. Consider this circuit. Let's find the Thevenin equivalent circuit. Since there are no independent sources, this is case 3. First, disconnect the load as we did earlier. Next, connect a test source across terminals A and B, either a 1-volt voltage source or a 1-amp current source. Here, I'll use a 1-volt voltage source. To find the Thevenin resistance, we need to calculate the current supplied by the test voltage source. Let's mark the currents in each branch. First, apply KCL to node X. The current entering the node equals the current leaving. Then, apply KVL to loop 1, where I2 is minus 0.25 amps. Next, apply KVL to loop 2, noting that the voltage across the dependent voltage source is 3 times I1. We calculate the test current as 0.833 amps. Now that we know the test voltage and current, we can calculate the total resistance, which is equal to 1.2 ohms. This is the Thevenin resistance. If you use a current source instead of a voltage source, you would calculate the voltage across it and then find the resistance. Since there are no independent sources, the Thevenin voltage is 0. The Thevenin equivalent circuit consists only of the Thevenin resistance, as shown. That's all for today. If you think my contents are valuable to the world, you are welcome to join my Patreon community. Like and subscribe to Professor Mad for more interesting videos.